In this video, I am going to explain you about the isomorphism, definition of isomorphism. So here we have to take two vector space. So I'm taking here u and v be two vector space over the field f. Okay, then I take a mapping f from u to v, which is already a linear transformation or vector space homomorphism. Then this mapping is said to be an isomorphism. Okay, this mapping is said to be an isomorphism if f is 1 1 as well as on 2. Now if there exists at least one map from u to v which is an isomorphism, then we say that u is isomorphic to v. So that was the definition. First of all, f should be a vector space homomorphism or linear transformation, and f should be 1 1 as well as on 2. So if we can find any mapping from this one vector space to another vector space which is satisfying these three conditions, that is, first it should be a vector space homomorphism, second it is 1 1, and the third it is on 2. If it satisfies these three conditions, then these two vector space will be isomorphic to each other. Now I'm do this theorem. We have this f from u to v is already an isomorphism. Okay, it is already an isomorphism. Then you have to show f is invertible. Okay, f is invertible, and also we have to show f inverse is also an isomorphism. Okay, isomorphism. So we have to show f is already given. Okay, so we have already what is given here. F from u to v is an isomorphism. So this is already an isomorphism. Okay, isomorphism. This is already an isomorphism. Since this is an isomorphism, means this is 1 1. This implies f is a homomorphism. First of all, homomorphism. It will be f is 1 1 and f is on 2. So this three condition is satisfied by this mapping. So this thing we know. Okay, so any map which is 1 1 and on 2 will always be invertible. Okay, since f is 1 1 and on 2, this f is invertible. Hence f is invertible. Any function which is 1 1 and on 2 is always invertible. So f is invertible, and we got an invertible function, so we define this invertible function as f inverse, and f inverse is from where to where? It is from v to u. Now you have to show this mapping is a vector space homomorphism, or it's an isomorphism, not a vector space only. You have to show that it is an isomorphism. Okay, so first of all we try to show it is a vector space homomorphism. Okay, so I take two element from V. Okay, I'm taking two element from V. Since if I take this, okay, this mapping, we have this is U, this is V, and here we have a mapping F. Okay, so I take two element here, A and B. So there should be some element in U. I took, okay, some element in U which is sent to V, to A. Okay, in the same way this element will be sent to B. So there exists xy belongs to U such that f of x is A, f of y is B. Okay, this implies x is equal to, means this is same, x is nothing but f inverse of A, and y will be also f inverse of B. Okay, now if I take this, I have to show it is a vector space homomorphism. Okay, it is a vector space homomorphism, means I have to show this f inverse of A plus B, this equal to f inverse of A plus f inverse of B. In the same way, also I have to show that f inverse of alpha A is equal to alpha f inverse A. So we have to show this. If we can show these two conditions, then f inverse is a vector space homomorphism. Okay, so I take this f of x plus y. So since f is a vector space homomorphism, this can be written as f of x plus f of y. Okay, this can be written as this. Now this f of x is what? What is your f of x? F of x is a. So you take here a. What is your f of y? F of y is b. Okay, so we get here. Now you composite with inverse. You apply inverse to both sides. So we have f inverse composite f applied on x plus y. Here also I'm applying inverse on both sides. F inverse applied on a plus b. So this is identity function, which is same as x plus y, which is equal to f inverse applied on a plus b. So what is your x? X is f inverse a. So f inverse a plus f inverse b, which is equal to f inverse a plus b. So we got the first condition already. Now we'll try to prove the second condition. So we'll take here, we are taking this f of alpha x. Now since f is a linear transformation, alpha applied on x. So we get alpha fx by using the second definition of linear transformation. We can write this. Now this, you apply inverse to both sides. Composite with inverse, we get f inverse f applied on alpha x. And this will be alpha you can take before this, we have alpha. What is your f of x? F of x is a. So we have here a. Okay, so we got here a. So we have here alpha a. Now I'm applying f inverse to both sides. So we get f inverse of alpha a. So this is your identity. And this we get as alpha x, which is equal to f inverse alpha a. Okay, alpha a. Alpha x is what? X is nothing but f inverse a, which is equal to f inverse alpha a. So we got here. We also proved the second condition. So f is a vector space homomorphism or is a linear transformation. So we have proved. Now we have to show that f is 1 1 and on 2. We have to show f is 1 1 and on 2. So we are taking, I'll take two elements which is same. So f inverse, I'll take here f inverse of a equal to f inverse of b. I have to show a equal to b. So f inverse of a is nothing but, we have done here already. What is f inverse of a? We have shown here f inverse of a is x and f inverse of b is y. So let us substitute this value here. So we get here f inverse of a is x, this is y. Okay, now f is already 1 1. We know f is 1 1, so we can write x equal to y is same as f of x equal to f of y, since f is 1 1. Okay, since f is 1 1, we can write this. Now what is f of x? F of x is a and f of y is b. So we got a equal to b. So this shows that f inverse is 1 1. So we have shown that f inverse is 1 1. Now we want to show it is on 2. Okay, so 2 on 2, if I take any element in V, okay, if I take any element in V, then since f is on 2, since f is onto, I'm using the condition here, f is onto, there exists x belongs to u such that f of x is a. Okay, we have this, f of x is a. Since f is onto, here I'm using the condition that f is onto. Okay, then I can write this. If f is not onto, I cannot say this. Okay, I cannot say it. I have taken one element here. So we have this is your mapping here. Suppose this is u and this is your v. So I took one element here, but this element is mapped only if f is onto, will be mapped. So since f is onto, we have already this f is onto, there should exist one element x in u which is sent to a. So we have here, I took one element in v, there exists x belongs to u such that fx is a. Now we got here fx is a, this implies what? F of x is what? A. Now if I apply with inverse on both sides, f inverse composite f applied on x is equal to f inverse a. Okay, f inverse a. So this is x equal to f inverse a. Okay, so this we got x equal to f inverse a. So I took one element in u. Okay, so f inverse, let us check what is f inverse. F inverse is a function from v to u. So I have taken one element in u. Okay, I took one element in u. I find that the image is in v. Okay, so therefore f is onto. F inverse is onto. So we have here f inverse is onto. Okay, hence f inverse is an isomorphism, because we have proved already it is 1 1, it is onto, as well as it is a vector space homomorphism. So therefore f inverse is an isomorphism. It's an isomorphism. Okay, it's an isomorphism. Thank you.